we're going to introduce something called the cumulative distribution function. And just to get warmed up, I want you to write in our shorthand notation these three probabilities. The probability that water freezes is the probability that our event temperature is less than or equal to 0. You could have also interpreted this as the probability that the temperature is equal to 0. One of the nice things about the mathematical notation is it disambiguates these two ideas, whereas if we're just speaking, we might have some ambiguity. The probability that it's at most 10 degrees is the probability T is less than or equal to 10. And the probability that it will be at most 20 degrees is the probability T is less than or equal to 20. So the odds of water freezing, the odds that you'll definitely need a jacket, the odds that you probably won't need to wear shorts, say. Now these all have the same format, probability T less than or equal to something, and the only thing that's changing is this number. And so if I were going to ask a lot of these questions, it would make sense to define a function where f of x would be defined as the probability that the temperature is less than or equal to x. So let's go ahead and define that function. In that case, PRT is less than or equal to 0. That would just be f of 0. PRT is less than or equal to 10. That would be f of 10. And PRT is less than or equal to 20. That would be f of 20. Now I want to mention this seems like a very specific thing to define. It ends up being extremely useful, which is why we're spending time on it now. This is called the cumulative distribution function. We like to use a capital F to denote it, and its definition is just exactly what we did before. F of x is just shorthand for the probability that my event is less than or equal to x. Let's stick with temperature at noon tomorrow, because this is a fairly intuitive thing. So I have these values, and remember this is just shorthand. So f of 0 is the probability that the temperature tomorrow is less than or equal to 0. F of 100 is the probability that the temperature tomorrow is less than or equal to 100. What I want you to do is put these in order from smallest to largest. Now pause the video, take some time. This takes a little bit of thought, but it's a useful experiment for understanding what comes next. So some of these are fairly intuitive. It is almost certainly not going to be more than 100 degrees Celsius. If this were Fahrenheit, this would not be so certain. But the probability the temperature is less than 100, pretty certain. The probability that the temperature is less than negative 100, that's pretty much 0. This is very extremely cold temperatures. This is like physics experiment level cold temperatures. The odds of this happening are very low. On the other hand, the odds that it's freezing, I mean, depending on when you're listening to this, yeah, it could be freezing, could be not. Let's say that's definitely not 0, definitely not 1, definitely somewhere in between. So these three I can order pretty easily. F of minus 100 is the smallest. F of 0 is in the middle. And F of 100 is higher than these. And now we're left with 2. And these start to look a little bit similar. So the probability that it's less than 200 degrees, it's probably going to be less than 200 degrees. This is probably pretty close to 1. So this probability and that probability are starting to look pretty similar. So how can we differentiate them? Well, maybe they're both exactly 1. Maybe there's some crazy solar event that's going to happen and one is more likely than the other. Let's think about what it means to be cumulative. I said this is a cumulative distribution function. So here's all of our possible temperatures, 0, etc. And if let's say I have a time machine and I run a bunch of trials where in one trial I see what the temperature is tomorrow, and in another trial I see what the temperature is tomorrow, and another trial I see what the temperature is tomorrow, and I record the temperatures. So maybe on my first trial my temperature tomorrow is 5, and on the next one it's 7, and then it's negative 2. And every time I run this trial I record what the temperature is. Well, if it never makes it above 100, then 100% of the time my temperature is less than 100, and automatically then 100% of the time my temperature is less than 200 as well. If there were to be some horrible event, maybe a nuclear blast, and we somehow got a temperature in here, then this temperature would be counted in f of 200. F of 200 counts the proportion of days where the temperature is less than 100. It would not be counted in f of 100. So if f of 100 and f of 200 are not the same, it must be the case that f of 200 is bigger. For similar reasons, it must be the case that f of negative 200 is smaller than f of negative 100. Again, both of these seem pretty close to 0, but if, and maybe they both are 0, but if they're not the same, we have no choice but to say f of negative 200 is less than f of negative 100, because if there were some horrible heat death of the universe day where we were between negative 100 and negative 200 degrees, f of negative 200, that's the probability that my temperature is less than 200 degrees, so that counts all the days up to here, doesn't capture that one data point, but f of negative 100 does. F of negative 100 is all of these days, and so it would capture more. So that's why we can confidently say f of negative 200 is less than or equal to f of negative 100. And this argument, by the way, no longer has to be restricted to temperature. Any variable at all, no matter how it behaves, if I take this cumulative distribution function, I'm going to have f of negative 200 less than or equal to f of 100, and f of 100 less than or equal to f of 200. So now let's think of just a totally random event. I have no idea what it is. Maybe it's temperature, maybe it's coin flips, maybe it's something totally else. I have no idea. I can still order these cumulative distribution functions from smallest to largest. F of negative 2 captures every single event where my value is in this purple range, whereas f of negative 1 captures every single event where my value is in this purple range, and that's a bigger range. So f of negative 2 is less than or equal to f of negative 1. And this continues on. F of negative 1 captures these events, f of 0 captures these, so f of 0 is greater than or equal to f of negative 1. So what we find is that we have a non-decreasing function. The cumulative distribution function, which remember is just shorthand for the probability that my event is less than or equal to this variable, is a non-decreasing function. It never goes down. It might stay the same. It can go up. So that's our first property of the cumulative distribution function. There's 3 other properties that we can think about. The second one is, because this is a probability, on the very first slide of probabilities, we said a probability is a number between 0 and 1. So this function is always between 0 and 1. The 2 other properties I want to talk about have to do with limits. I'm going to write this very informally. So very informally, infinity is not a number, but if it were, if I were to take f of infinity, I'll put scare quotes because this isn't really something we could do, this would look like the probability that my value is less than or equal to infinity. That should be 1. If I get a number, it's always going to be less than or equal to infinity. Similarly, if I could think about plugging in negative infinity here, I could think of this as the probability that I get some number and it's less than or equal to negative infinity. That one never happens. Okay, so these don't work because I'm not allowed to plug in things that aren't numbers into my function. What I can write and be formally correct is the limit as x goes to infinity of my cumulative distribution function is 1. And the limit as x goes to negative infinity of my cumulative distribution function is 0. So these are 4 properties that every cumulative distribution function must have. And for our purposes, we're going to say if you have any function that makes these 4 things true, that is a cumulative distribution function. Let's practice using the notation again, just real quick. Let's suppose you take a bunch of samples on a bunch of days and you record the temperature. Half of them are less than or equal to 20 degrees, 2/3 of them are above 10 degrees. You should be able to find numbers for f of 20 and f of 10. Pause the video, write down those numbers, and then come back to me. all we need for this is the definition of a cumulative distribution function. This is the probability that my event, whatever it is less than or equal to 20. This is the probability that my event, whatever it is less than or equal to 10. If I look at all my days, half of them are less than or equal to 20, so this probability is 1/2. 2/3 of my days are above 10 degrees, so that means the remaining 1/3 are below 10 degrees. So it's a little bit arbitrary that cumulative distribution functions are less than as opposed to greater than, but what you see in this second line is that actually we can swap between less than 10 and greater than 10 fairly easily.